In this how-to video I'm going to explain the basic principles of nuclear magnetic resonance, and I'm basically going to be talking about carbon NMR and hydrogen NMR, and this introduction is really going to give you an overview of how it works. I'm not going to go into any deep chemical ideas or principles or explanations. Just a basic overview of how the process of nuclear magnetic resonance works. And there is some stuff you need to know which will get examined on A-level syllabus, and there's the stuff that you don't need to know, but actually knowing it helps you understand the other stuff. So that's where I'm going to begin. So this is the stuff we don't really need to know but helps with our understanding. The first thing is, when we're talking about NMR, is we're really talking about carbon-13 and carbon and hydrogen. And the reason is this: if we look at carbon-13, if we look at its nuclear structure, it's got 6 protons and 7 neutrons. And if we look at hydrogen, it's just got a single proton. Now, we can envisage that protons and neutrons behaving much like electrons in that they have spin. So, in the nucleus of a carbon atom, carbon-13 atom, we have 6 protons with spin and 7 neutrons with spin. And it's helpful to imagine that the spin of the protons is in one direction, let's say clockwise, and the spin of the neutrons is in the opposite direction, anti-clockwise. So the effect is to cancel each other out. But this is why it's important, and this is why we're talking about carbon-13 and we're talking about hydrogen-1. In carbon-13, with the 6 proton spin is cancelled out by the 7 neutron spin, but there is 1 neutron over, which means there is some residual spin. And in the hydrogen nucleus there is 1 proton with spin. There are no neutrons, so there is nothing to cancel out the proton spin. And we can envisage this proton in the case of the hydrogen and the neutron in the case of the carbon-13 as behaving like a little tiny bar magnet. So how do we progress that further? Well, let's think about our carbon-13, for example. If we were to put a carbon-13 atom inside a magnetic field, and here we have a magnetic field, we can consider there are 2 possible states. There is a state where the little bar magnet created by the spin in this carbon nucleus is lined up with the magnetic field. And we can imagine that then that this atom has a low energy because the magnetism, the little bar magnet in the nucleus, is lined up and matches the magnetic field. Whereas this carbon atom hits a magnetic field, it's spinning in the opposite direction, so this magnetic field is in the opposite direction, it's against the magnetic field. So in this case, this atom is at a higher energy because the magnetic fields don't align. So we've got a low energy state where the magnetism lines up, and we've got a high energy state where the magnetism do not line up. So what way forward now? Well, if we give some low energy radio waves, in other words a low energy source from radio waves, to carbon atoms which line up, whose magnetism lines up with the magnetic field, we can effectively get this magnetic field of the carbon atom to flip into a high energy state. So at the appropriate frequency, depending on what environment this carbon is sitting on, in other words, what type of carbon molecule it is, what's surrounding it in terms of hydrogens, oxygens, etc., in its molecular structure, we can get the magnetic field of this atom, to flip from a low energy state to a high energy state, and we call that excitation. But when we've excited it, what then tends to happen is that it will fall back from the excited state back to the low energy state, and we call that relaxation. So just quickly running through that, we give the atoms low frequency radiation, radio frequency energy basically, and at some point the frequency reaches a level where it causes the little magnets in the carbon atoms, or some of the carbon atoms, to be excited to from the low state where they line up with the magnetic field to a high energy state where they're against the magnetic field. And once they get to this state, then what happens is they invariably fall back to the low energy state, and at that point they release the energy which has been given to them, and this is called relaxation. And the energy is given out, and we can detect this. So if we keep giving these atoms the same frequency of radiation, what happens is we have a continual state of excitation and relaxation. And this continual excitation and relaxation we refer to as resonance. So the atoms, the magnetic state of these atoms, are resonating between high and low energy states. And that's nuclear magnetic resonance in a nutshell. It's nuclear because it refers to the nucleus of the atom. It's magnetic because it refers to the magnetic state of the nucleus, either lining up at low energy or against high energy. And it's resonance because it's resonating between low energy and high energy states. So nuclear magnetic resonance. And in principle, that is all nuclear magnetic resonance is. So now we move on to the stuff that is likely to be examined, and you will be asked questions in most A-level syllabus. We refer to a property called chemical shift, and chemical shift is given the symbol delta. And it's, put simply, it's the place in the nuclear magnetic resonance spectrum where the nucleus absorbs energy. In other words, it's that point where resonance takes place, like I've just explained with the diagrams. Now, this is normally calibrated on what we call the delta scale. So we've got a chemical shift which is calibrated on the delta scale, and it's measured in units of parts per million. So how do we arrive at that scale? How do we calibrate that scale? Well, we have to have some reference point. So chemical shift is measured relative to a reference signal from a standard compound called TMS. And TMS stands for tetramethylsilane. And this is a chemical which is introduced into the sample before we do NMR spectroscopy. And what that does is it gives us a strong base signal which equates, or is made to equate, to a delta shift, a delta chemical shift of equal to 0, and everything else, every other peak that we get, is referred to or referenced relative to this TMS signal, which is arbitrarily set to delta 0 ppm. So that is fundamentally what chemical shift is. It's very important that you remember that chemical shift is 1 given the symbol delta. It's measured in units of parts per million, ppm, and chemical shift is referenced next to a standard, which is TMS, tetramethylcyanine, and TMS gives us the standard, which is set to delta equal to 0 parts per million. The other thing which regularly arises in questions about NMR is the types of solvent. Now, NMR is carried out in solution. So when we measure an NMR spectrum of a carbon compound, we invariably put it into a solvent. But this is where the problem arises, because most solvents contain hydrogen atoms and carbon atoms. And because hydrogen has it's only got one proton, well, obviously hydrogen produce a signal, an NMR signal, because it effectively behaves like a little magnet, much like the explanation that we've previously given for carbon. So what we have to do is, when we run NMR spectra, we have to get round this hydrogen problem in solvents. And the way we do that is using solvents which are called deuterated solvents. And in this case, the solvent, the hydrogen in the solvent, isn't hydrogen, it's actually deuterium. And if we remember what deuterium is an isotope of hydrogen, but it has one proton and one neutron. And because it has one proton and one neutron, the spin of the proton is counteracted by the spin of the neutron. It's an even number of nucleons, and because the spins are opposite, they counteract one another, so effectively there is no signal produced in the NMR spectrum. So deuterated solvents do not themselves produce signals in any NMR spectra. And finally, the most common solvent to remember, and is often referred to in A-level examinations, is CdCl3. And it's worth remembering this solvent. Here we've got a carbon, we've got an atom of deuterium, and we've got 3 chloride atoms, chlorine atoms, forming a molecule which is a common solvent. So I hope that's helpful. We've gone through how it works, which for all intensive purposes you shouldn't get asked questions on, but I hope it helps you understand the principles. And we've gone through the bits that you do need to know something about, which is chemical shift and solvents, and the whys and wherefores of using deuterated solvents. Thanks.